ಎಸ್ ಅಂತ ಹೇಳಿ ನಾನು ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ. A very good afternoon to all of you. Myself, Dr. Sandeep R, and my colleague, Professor Kavya AP, would be handling the electromagnetic session. Okay, the plan would be like this. First, we will be covering the overview of the course. So first we'll be doing overview. Followed by the early quiz. Once we cover the basic concepts, we'll be giving the early quiz. So around 5 to 8 minutes for completing the early quiz, and then followed by again discussion of previous year problems, and finally the end quiz to check what's your level of preparation. So this would be the plan of action for this particular session. Okay, so let me start with the overview. As you all know that the entire electromagnetics can be said as one is the electrostatics part and the other one is a magnetostatics part, and the remaining portion is nothing but the time varying fields where we come across both the electric field as well as the magnetic field. Okay, so the basic laws of the electrostatics are nothing but the Coulomb's law and the Gauss law, right? So let's start with the Coulomb's law. So okay, now suppose they have a reference point, say the origin, and at a distance of say R1, this is the vector R1. Say I have a point charge Q1, and again I have another point charge Q2, which is at a distance of say R2 from the origin. So this is the position vectors, say R2. Okay. Now whenever and let me assume further that these two charges are point charges, they are at rest or they are static, and they are of both are positive charges, and definitely you know that they will experience some force among themselves. So what is that force experienced between these two point charges when it is placed in? We'll assume that it is currently in the free space, and what is the force experienced, right? Suppose I want to calculate what is the force experienced by point charge 2 due to Q1. So let me assume that it is in this direction, then it is represented as F12. So force on point charge 2 due to 1, and if I assume that it will be along this particular line, so it's opposite direction, then what is the force on point charge 1 due to 2? So okay, so this will be F21, both are vector quantities, and this is the line joining them, again a straight line. Please assume this to be a straight line. Say first let me write an equation for the force. What is the force acting on point charge Q2 due to Q1, and say suppose this is the distance between Q1 and Q2, which is represented by capital letter R, that's the vector. So if I write the equation as per the Coulomb's law, it is F12, the force, which is equal to, it is directly proportional to the product of the point charges, which is nothing but the Q1 and Q2 by the 4, and inversely proportional to the square of the distance between them. So here we are trying to represent it as removing the proportionality constant. We would get 4 pi epsilon naught. So I'm removing those steps and I'm directly writing it. So it is 4 pi epsilon naught, and which is nothing but the R12 square and unit vector AR12, where R12 is nothing but the vector which is equal to the R2 minus R1 and the magnitude of R12 which we have written here, R12 vector magnitude is written as R12. Okay, so and unit vector, you know, vector itself by the magnitude. So here the unit vector AR12 unit vector itself which is R12 vector by the magnitude, so which is R12 magnitude or just R itself. So this is the vector form of Coulomb's law. Some of the important points that you need to take care of is that that F21 will be equal to minus of F12. So it is opposite one. That is the force experienced by point charge Q1 due to Q2 is exactly opposite in a direction with respect to F12. Magnitude would be the same thing. And I have already told you that those two things should be point charge and they should be at rest. So for like charges, you know that like charges would repel and like charges would attract, and the product of Q1 and Q2 will be greater than 0 for like charges, and Q1 into Q2 will be less than 0 for unlike charges. So these are the important things that you need to remember about with respect to the Coulomb's law. Continuing further, let's define the electric field intensity based on the Coulomb's law. So electric field intensity is denoted by E. It is defined as the force per unit charge, and it is given by the expression, say E is equal to Q by 4 pi epsilon naught R, 4 by epsilon naught R square into unit vector AR. Again, I can write the unit vector AR as the vector by the magnitude of the vector, which I clear to, and this is for the point charge. Continuing, if I want to, suppose I have a continuous charge distributions and I want to calculate the total charge, then we can say, suppose in the first case I have a line charge, then I want to calculate what is the total amount of the charge, then it is given by the line integral of rho L dl. Okay, so this is nothing but rho L represents the line charge density. Okay, so suppose if there is a surface charge, then I can write it as this for line charge. So Q is equal to surface integral. When I am writing surface integral, it is understood that it's a double integral, and rho S represents the surface charge density and ds. And finally, the total volume charge is nothing but the volume integral, which is nothing but the triple integral rho V, the volume charge density dV. Okay, so this is how we try to obtain the total charge. Now, suppose I want to calculate the electric field intensity due to any of these type of charge distribution, then we know that E is given by Q by 4 pi epsilon naught R square, right? In place of Q, you will be replacing it with, say, line integral of rho L dl, or surface integral of rho S ds, or volume integral of rho V dV for the line charge, surface charge, and volume charge respectively. Let us consider one particular scenario. Say, suppose I have an infinite line charge, then the electric field intensity is given by E is equal to rho L by 2 pi epsilon naught rho into unit vector A rho. Here, rho represents the perpendicular distance between the line charge and the point of interest. Okay, so suppose say this is these are the three axes, and say suppose I have the line charge along the z-axis, and my point of interest is this particular thing, then I'll draw a perpendicular distance from the line charge to the point of interest, and this becomes the rho, the distance between the line charge and the point of interest. Okay, now another particular scenario, what if I have a infinite sheet of charge? The electric field intensity at a particular point due to infinite sheet of charge is given by E is equal to rho s by 2 epsilon naught, sorry, 2 epsilon naught into unit normal vector n. To stress on this, what I'm trying to say is, say suppose I have say the the 3-axis. Say this is x, this is y, and this is z, and say I have an infinite sheet. Okay. So say parallel to YZ plane, okay, parallel to YZ plane, and my say point of interest is somewhere here. I'm interested in determining the electric field intensity at this particular point. Then the unit normal vector to the from this thing. So this will be the direction of AN. Suppose I want to determine behind this, then it will be minus AN because it is pointing in the negative x-axis. Okay. So we have been talking about the electric field intensity. We have another important quantity in electrostatics. That is nothing but the electric flux density, which is represented by D. And the relationship between the electric flux density D and the electric field intensity E in free space is nothing but T is equal to epsilon naught into E, where epsilon naught is nothing but the permittivity of free space. Okay. So which is given by 8.854 into 10 power minus 12 farad per meters, right? And okay, the electric flux, if I suppose I want to determine what is the total electric flux from a closed surface, yes, then it is given by say psi is equal to surface integral of d dot ds. So I only consider those components which are those components of flux which is normal to the surface. If it is not, then I would try to determine that component of flux along the unit normal vector. That is why the dot product, which is nothing but d dot ds, and I cover the complete surface area, then I would get what is the total flux. Okay. Now let's go to, so we have finished the Coulomb's law, and then the important parameters such as what is the force between the point charges, electric field intensity, then the electric flux density in free space. The next important fundamental law of electrostatics is nothing but the Gauss law. Okay, so let's try to state the Gauss law and then write a mathematical relationship. Okay, Gauss law states that the net electric flux penetrating a closed surface is equal to the total charged enclosed. So mathematically, it's nothing but psi is equal to Q enclosed. So that means what, psi is also measured in coulombs, Q is also measured in coulombs, and more generic way, we know that psi is nothing but d dot ds. So surface integral of d dot ds. And what is Q? Q is nothing but the total charge. Here we have seen how can we determine a total charge if it is a line charge, surface charge, and volume charge. But more generic form would be the volume charge, and I would write Q is nothing but the volume integral of rho v dv. So please remember, this equation seems complicated, but remember this is nothing but the psi, which is nothing but the total flux. This is nothing but the Q, which is nothing but the total charge. It only says that whatever the flux coming out of the closed surface area is equal to the charge enclosed within it. Okay. So going further, we can have the first Maxwell's equation, which is nothing but del dot D is equal to rho v. So this is nothing but the divergence of the electric flux density would give me the volume charge density. Now, whenever you are applying the Gauss law, you would make sure that we have a symmetric charge distribution, because whenever there is a symmetric charge distribution, our life becomes simple and all our calculations would be easy. Because we consider a Gaussian surface such that the D is either perpendicular or parallel to the surface. So because our integration will become simple, and that is why we restrict those conditions. And determination of electric field intensity or electric flux density when there is a distribution, when there is a symmetry in the charge distribution, then it is quite easy for us to do the calculations. Then you may ask, what if I do not have the symmetry in the charge distribution? Then of course I have to go back to the basic law, which is nothing but the Coulomb's law. Okay. The other way is that, say, suppose I consider the differential form of Gauss law. So I'm considering a very small, infinitesimally small volume element, differential volume element, and then try to apply Gauss law to it because it exhibits the symmetry, and then try to determine it. So that's another way of doing it. Otherwise, you can just go for the basic law, which is nothing but the Coulomb's law. So let me state at this point, what is the divergence theorem? Divergence theorem states that the total outward flux of a vector field D through the closed surface S is same as the volume integral of divergence of D. I think not that great deal. So just let me write what was the Gauss law. Let me go to the previous slide. Here we have, right? So left hand side we have surface integral of D dot ds. In the right hand side we have the volume integral of rho v dv. Just now we have learned that divergence of D will give me the volume charge density. So using that, I can write that surface integral of D dot ds is equal to the volume integral of divergence of D. So that's why it states that the total outward flow, outward flux of a vector. So this is the total outward flow of a vector through a closed surface. This is the total flux. It is same as the volume integral of divergence of D. So that is what it is trying to tell. Moving on to the next concept, how do we determine the total work done or the electric potential energy required to move a point charge Q from one point, say point A to point B in the presence of electric field intensity E. So the equation is nothing but W is equal to minus Q into integral A to B E dot dl. So okay, so this would be the formula for calculating the work done. And continuing further, the potential at say at a distance of r from the origin due to a point charge q, which is at a distance of r prime. So let me try to show you visually. So I have this say x, y, and z. What I'm trying to say is, so I want to determine the potential at r. Say this is say vector r. This is the point of interest, and the point charge q is at r prime. Say, and let me consider another vector. This is a point charge q, and its distance is say r prime. Then what is the potential at r due to a point charge q at r prime? When I say r and r prime, these are the distances which are measured from the origin in the say given coordinate systems. So then that is given by v of r is equal to q by 4 pi epsilon naught vector r minus r prime vector magnitude plus some constant c. Now I'll tell you, I told you that if there is a symmetry in the charge distribution, then the calculations would become easy in terms of when we are applying Gauss law. If there is no symmetry in the charge distribution, if there are multiple types of charge distribution, then we would have to definitely go for the Coulomb's law. But the problem with Coulomb's law is that we are dealing with all the vector quantities, right? The electric field intensity E, the electrostatic force F, and electric flux density D. Everything is a vector quantity, and all whatever we do calculations is vector. Then you might think, is there any scalar quantity from which I can determine the other parameters such as E and D and so on? Well, that's the question, right? So the answer to that question is definitely yes. We have the quantity, and that is nothing but the electrostatic potential E, electrostatic potential V, from which we can determine E, D, and so on. So this is nothing but V. So V plays a very important. Here we assume that we know the potential of any surface at all points, from which I know from V I can determine E we'll see that relation. What is that relation used? Once we know E, we can determine D. But please remember, this V is a scalar quantity. So once we have the scalar quantity for a given configuration, we can determine the other vector quantities, namely E and D. Of course, then you would ask the question that, fine, I have this, but what is that I can use, the equation that I can use from which I can determine E using V? And the equation is nothing but the electric field intensity is nothing but the negative potential gradient. E is equal to minus del of V. Please remember, V is a scalar quantity. Del is nothing but the del operator. We are applying the gradient. So suppose V is in the Cartesian coordinate system, then del would be dou V by dou x plus dou V by into unit vectors. So let me write this. So del is equal to just the del operator. So dou by dou x into unit vector ax plus dou by dou y into unit vector ay and plus dou by dou z into unit vector az. I am trying to determine the gradient of V, then it is V dou V by dou x, dou V by dou y, dou V by dou z into unit vector ax, ay, az respectively. So minus of this. So from this we can determine E. Once I know E, I know that D is nothing but epsilon naught into E. So I can determine D. That's how we can do it. Okay. So another important thing that I would like to say here is that suppose I want to determine the potential difference VAB, that is the potential at B with reference to A, then it is nothing but VAB, which is given by minus integral of A to B E dot dl. So which is equal to W by Q, which is work done in moving a point charge from say point B to point A. So which is equal to VB minus VA, that is upper potential, higher potential minus the lower potential. Okay. So with this, okay, the last thing that that is important in terms of the electrostatics is concerned is the electrostatic energy. The electrostatic energy equation for electrostatic energy is WE is equal to half into summation K is equal to 1 to N. So I'm assuming that what is electrostatic energy due to N point charges in the vicinity. So this is nothing but QK into VK. VK represents the potential of at each particular point. And for a continuous volume distribution, this is for discrete, right? Suppose I have a continuous volume charge distribution, then WE is equal to half into volume integral of D dot E dV, okay, which is also equal to, since we know the relationship between D and E, you can write, so which is nothing but again the volume integral of epsilon naught into magnitude of E square dV. Okay, so this is how you can calculate the electrostatic energy. Now coming to the materials. So materials can be classified roughly as conductors if the conductivity is very much greater than 1 and the relative permittivity is equal to 1. And it can be said as dielectrics, the materials, if sigma is very much less than 1 and the relative permittivity is greater than or equal to 1. So this is in terms of the electrical properties. So where I've already told you, sigma is the conductivity and epsilon r is the relative permittivity or the dielectric constant. Okay, so moving on to the next topic, the electric current is the flux of electric current density, which is nothing but in terms of equation, I is nothing but determined by surface integral of J dot ds. Okay, so next important thing is the resistance of a conductor is of a uniform cross section is nothing but R is equal to L by sigma into S, where L represents the length of the conductor, S represents the surface area, the cross sectional surface area, and the sigma represents the conductivity. It is very simple because R is directly proportional to L and inversely proportional to the cross-sectional area, removing the constant of proportionality, which is given by 1 by sigma. Okay, so that's the formula we have. And we have related D and E in free space. Similarly, we can try to relate D and E in other media, that is where D is equal to the general equation, D is equal to epsilon into E, where epsilon is nothing but epsilon naught into epsilon r. Epsilon naught is the absolute permittivity and epsilon r is the relative permittivity of the medium into E. Okay. The other important thing that I would like to tell is the electric susceptibility, which is denoted by chi E. It's given by, it is equal to epsilon r minus 1 of a dielectric. Epsilon r is the relative permittivity of the dielectric constant. It measures what is this electric susceptibility of a dielectric. It gives you the sensitivity of the material to an electric field, how susceptible it is or how sensitive it is to an electric field. Okay. Okay, so let me write another important equation, which is nothing but the continuity of equation. So the principle of charge conservation, that is the basis of Kirchhoff's current law, is stated in terms of the continuity equation, which is nothing but the del dot J, that is the divergence of J, is equal to minus of dou rho V by dou T, or del dot J plus dou rho V by dou t is equal to 0. This is the continuity equations, or which forms the basis for the Kirchhoff's current law. We also have the Ohm's law here, which is nothing but J is equal to sigma into E. Okay. So where J is the current density and sigma is the conductivity and E is the electric field intensity. Now, whenever the electric field conducting material is placed, now I'm interested in determining what happens to the electric field intensity or the electric flux density when it moves from one medium to another medium. Say, suppose I have two dielectric mediums, then what boundary condition does it satisfy when the E or D moves from one medium to another medium? Say, suppose I consider a dielectric interface, then I can say that the E tangential components of E is equal to are the same. That is, it is continuous. That is, the tangential components of E will be continuous, or it will not undergo any change when it moves from dielectric medium 1 to dielectric medium 2. Whereas the electric flux density, of course, when I say this, the normal component of E is also not continuous. So D1N, which is nothing but the electric flux density in medium 1, is minus D2N, the normal component of electric flux density in medium 2, is equal to the surface charge density. Or if it is a free space or a charge free region, then I can write D1N is equal to D2N, because rho s is equal to 0. For a dielectric conductor interface, then you can see that the tangential component ET is equal to 0, and dN, the normal component of electric flux density, is equal to epsilon naught into En, which is equal to rho s. Why all these things happen? Because E is equal to 0 inside the conductor. Okay, so now we said that, okay, if there is a symmetry, then Gauss law. If there is no symmetry, Coulomb's law. And if it is still complex, try to determine the potential, electrostatic potential, provided it is known at all points. But in a practical scenario, we may not know the potential at all the points. Then we may be knowing at certain points or at the boundaries. Then how do I determine the V? First, if I determine V, I can determine D, I can determine E, and so on, right? So first thing is, how do I determine the V? So for that, we will try to solve the Laplace equation or the Poisson equation. So for a non-homogeneous region, the Poisson equation is given by del dot epsilon into del of V is equal to minus rho V. If it is a homogeneous region, then epsilon is independent of space variables, then it becomes simple, and we can write the Poisson equation for homogeneous region as del square V is equal to minus rho V by epsilon. And If it is a charge-free region, when I say charge-free region, rho v is equal to 0, then the Poisson equation becomes the Laplace equation, so which is nothing but del square v is equal to 0. So now you may ask, is the solution unique to this? Yes, definitely, provided for the given boundary conditions, if certain V satisfies the Laplace equation or the Poisson equation, then that solution has to be definitely unique. But that is what the uniqueness theorem states. Once you know that we know the potential across the boundaries, we can solve Poisson and Laplace equation, try to determine V. Once we know V, again we can use the relation that electric field intensity is nothing but the negative potential gradient. We can determine E. Once we know E, we can determine D, depending on whether we are considering the free space or not, using the relationship between D and E. Okay. So the other useful applications of the Laplace equation is nothing but we can determine the capacitance of a particular object or a resistance of a particular object. So suppose I want to determine the resistance, then say suppose I have determined the potential difference V naught, I can determine, first my job is to determine I is equal to surface, right? But I have already stated the Ohm's law of here, right? So Ohm's law. We can write J is equal to sigma into E. Using that, I can write something about sigma into E dot ds. Once I find I can definitely determine R is equal to V naught by I. So this is how you can use the Laplace equation to determine the resistance of the object. Similarly, I can determine C. Say let me assume that there is some potential difference V naught between the plates of the capacitor. I can solve the Laplace equation. Once I do that, I can determine Q, which is nothing but the surface integral of d dot ds. So here d is equal to epsilon into E. I'm directly writing that because, let me repeat it, because Q is equal to surface integral of d dot ds. Don't forget this, because Q is equal to psi. So I have directly written that, and D is equal to epsilon into E. So I've written epsilon into E dot ds. So from this I can determine the charge. Once I know the charge, I can determine the capacitance is nothing but C is equal to Q by V naught. So this is the overview of the electrostatic part. Let us move to the magnetostatics. Okay, so moving on to the just like we had the Coulomb's law and the Gauss law as the fundamental laws of electrostatics, similarly we have the Biot-Savart's law and the Ampere's law in magnetostatics. Just like the Biot-Savart's law is analogous to, I cannot say analogous, but very near to that, or a cousin of that. So it is very analogous to the Coulomb's law, whereas the Ampere circuit law is analogous to the Gauss law. So let me try to say what Biot-Savart's law is. Conductor, say the current is flowing in this direction I, and I have a say differential current element which is represents say dl1. Okay, so dl1, this is a point 1. So whenever there is a current flowing, definitely it would produce some magnetic field intensity. Now I'm interested in determining at say point 2, what is the magnetic field intensity at point 2 due to the differential current element at point 1. Say now let me also further assume that this network issue. Yes, hello? Hello? Okay. Okay. Fine. Okay, there is some technical issue. Okay, so what I was trying to say I have a current carrying conductor, say this is I, and I'm considering the differential element dl, and say this is say 0.1, and say I have r from the origin, so vector r, and say I have the differential element which is at a distance of say r prime from the origin. Now I'm interested in determining the magnetic field intensity at point uh, 2 due to differential current element at point 1. So this is point 1, and the distance, this I'll represent it as a vector r12. Then as using the Biot-Savart's law, I can write it as dH2, that is differential magnetic field intensity at point 2 due to the differential current element I1 dl1 I1 dl1 I and dl1, the cross product with unit vector A r12 by the 4 pi r12 square. So here also you can see that it is directly proportional to the differential current element, and that is the current I and the differential current element, and inversely proportional to the square of the distance between them. So you can see that it is having a very close relationship between to the Coulomb's law. Okay, this is measured in terms of amperes per meter. Now, where R12 vector is nothing but similar to Coulomb's law, we had written there, so which is nothing but vector R minus R prime, vector R prime. And here, whatever I have written R is nothing but magnitude of R12. Okay, so this is R12 magnitude. Okay. Now, this is, I have considered a differential current element, right? What if I have the other types of current distributions? It could be the surface current distribution, it could be the volume current distribution. We have a relationship between the line current, surface current, and the volume current, which is nothing but say I dl is equivalent to K ds, which is similar, which is equivalent to J dV. Okay, so depending on the type of current distribution that you come across, you can replace that in the Biot-Savart's law and try to determine the magnetic field intensity at a particular point of interest due to an appropriate type of current distribution. Moving on to the next fundamental law of magnetostatics, which is nothing but the Ampere-Circuital law, which states that the circulation of H around a closed path is equal to the current enclosed by the path. Putting that in terms of mathematical equation, so contour integral of H dot dl is equal to the current enclosed, which is current enclosed. We know that I is equal to surface integral of J dot ds. So I can write this as surface integral of J dot ds. So this is what is that. Or circulation of H would give me the current enclosed by the path, right? So I can write using the mathematical notation, that is curl of H is equal to J. Okay, curl of H is equal to J. So using that relationship in the above equation, I would get the surface, the contour integral, line integral, which is the line integral H dot dl is equal to, instead of J, I can H dot ds. This is nothing but the Stokes theorem. This is nothing but the Stokes theorem, which states that the circulation of vector field H around a closed path L is equal to the surface integral of the curl of H over the open surface S bounded by L, provided H and del cross H are continuous on H. So here we said that line integral of H dot dl is equal to surface integral of curl of H dot ds in simple terms. That's it, nothing else. Here again, when we are trying to apply the Ampere circuit law, we make sure that there is some kind of symmetry in terms of the current distribution. Whenever there is a symmetry in the current distribution, again our calculations would become easy. We consider a virtual Amperian path wherein the magnetic field intensity is constant. It's either normal or parallel to it. We consider the H to be parallel in this case, so that our integrals is simple. So once we have the symmetry in the current distributions, we would go straight away for the Ampere circuital law. What if there is no distribution in the symmetry in the current distribution? Then you would go for the Biot-Savart's law. Again, you may ask a question, okay, again, we know that it is tedious to use the Biot-Savart's law. Do we have a similar kind of equation that is a scalar quantity, from which I can try to determine the other vector quantities such as H, which is nothing but the magnetic field intensity, or B, which is nothing but the magnetic flux density? Can I determine from a scalar quantity? Yes. To that, yes, the answer is yes, but not completely. There are some restrictions. We'll come to that later. But let me also discuss the other important thing, which is nothing but the flux. We also introduced the term flux, right? So the flux is denoted by phi or capital psi. So this is capital psi, which is equal to the surface where B represents the magnetic flux density. So psi is measured in terms of Webers. So whereas the magnetic flux density is measured in terms of Webers per meter square, the magnetic flux density, which is denoted by B. In free space, we have a relationship between B and H. Just like we had a relationship between D and D in free space, we also have a relationship between B and H in free space, which is nothing but B is equal to mu naught into H, where mu naught is nothing but the permeability of free space, which is nothing but 4 pi into 10 power minus 7 henries per meter. Okay, there we had the absolute permittivity, which is nothing but 8.854 into 10 power minus 12 farad per meter. Here we have the mu naught, which is nothing but 4 pi into 10 power minus 7 Henry per meter. Now, we know that, say, suppose you consider the bar magnet, you know that there always exists a north pole and south pole. Suppose you break that magnet into infinite number of pieces, you would get infinite number of north pole and south pole. So what I'm trying to say that there is no material, magnetic material in which there is only one pole, either north pole or south pole. Any object you take, it is always true. And hence, but here, see, when we had said Gauss law, which is, we can say that the flux originates from positive charge and terminates with negative charges, right? So there is something like origin. It is always continuous. This magnetic flux is always continuous. It completes or ends within itself. So putting all those things in terms of mathematical equation, I can write the capital psi or the phi, when the authors use phi, which is nothing but the surface integral of B dot okay, B dot ds is equal to 0. There we had like psi is equal to q, right? Because we would consider that psi was because of the point charges q. That is why we had written psi is equal to q in terms of electrostatics. But there is nothing like, no such source is found for the magnetic flux in case of the magnetostatics. So that is why the psi, which is the magnetic flux, is equal to 0. Now we are at the point wherein we can consolidate and tell the same thing. We can written as del dot B is equal to 0, the divergence of B, because B is always in the form of a circle. Okay, now we are at the point wherein we can write the Maxwell's equation for static, electric and magnetic fields. So let me write first the differential forms. So this is differential form, and the integral form. And what remarks I would like to give some remarks on it, and we are at that point. So first thing we came across was del dot D is equal to rho B, that is divergence of electric flux density is equal to volume charge density, and that was the differential form of Maxwell's equation. Is the integral of D dot ds is equal to the volume integral of rho V dV. So which is nothing but is also Gauss law. So I've written it as Gauss law. Okay. Now we said that similarly, let us complete the divergence concept. So del dot B is equal to 0. In terms of integral form, we had written the surface integral of B dot ds is equal to 0. That is non-existence of monopole. So non-existence of monopole. Okay. Now we know that electric field intensity is usually the straight lines, and hence the curl of E, there is no circulation for electric field intensity. So curl of E is obviously 0, and which brings out to that the conservative nature of electrostatic field which is nothing but E dot dl is equal to 0. The other interpretation of this equation is nothing but when you move a point charge from one point to another point and bring it back to the same point, then the total work done is equal to 0. That's one way of seeing it. And the other way is that it is a conservative nature of electrostatic field. So irrespective of the path, the work done is the same. So this talks about the conservative nature of electric field. Finally, the fourth Maxwell's equation would be the curl of H is equal to J. So that's what we have seen, because the curl indicates the circulation density. The curl of H is the differential form of the Maxwell's equation. The integral form is nothing but the Ampere's law, which is nothing but the line integral of H dot dl is equal to the current enclosed, which can be represented as surface integral of J dot ds. So this is nothing but the Ampere's law. Okay. So I had asked you that, right? So do we have the scalar quantity? Yes, there is definitely there. And using the same relation, H is equal to minus del of Vm, where Vm represents the scalar magnetic potential or magnetic scalar potential. And this equation holds good provided if J is equal to 0. That is surface, that is the current density is equal to 0. We also have the magnetic vector potential, which is nothing but B is equal to del cross A, where A represents the magnetic vector potential, and A should satisfy the condition that del dot A is equal to 0. So if that is the case, then we can determine the psi, which is nothing but the flux from this magnetic vector magnetic potential. So which is nothing but psi is equal to A dot dl. Okay, this is capital psi, where L is the closed path defining the surface. Now, we also have, just like we had come across the Poisson and Laplace equation, because the potential may not be known at all points and we may have the potential only across the boundaries, then we may also have to use the Poisson or Laplace equation, right? We also have the similar equations in the magnetostatics, which is given by, just like we had written there, del square V is equal to minus rho V by epsilon for a homogeneous region. Here we have the del square A is equal to minus mu naught into J. So we have just obtained all the relationship between the magnetostatics and the electrostatics. I think it's already now 3:45, 3:50. You'll be given some 10 minutes time to attend the quiz. But before that, I would like to add that just like we solved the electric circuits by using Ohm's law, KVL, KCL, right? We can also solve the system which contains the magnetic materials using the magnetic circuits by drawing the analogous quantities between the electric circuit and magnetic circuit. And similarly, then we can apply the KVL and KCL on the magnetic circuits. Okay. So with this, I think it's already 3:47. I will be given just a minute. Hold on. 10 minutes. So we'll give some 5 minutes now. 3:47. We'll join you back after 5 minutes. We will share the early link for the early quiz. I request Jaina, please share the early quiz to you. So we'll give 5 minutes time, and after that we'll quickly review the answers of early quiz in 5 minutes. We should complete all these things in roughly 4:45. So see you then back then. Okay. Thank you. So I'll join after 5 minutes. last 1 minute. We will be, I think, 6 to 7 minutes would have been given. So in less than a minute, we'll be quickly reviewing the early quiz answers and why it should be. Okay. Okay. Okay, fine. Okay, let's discuss the answers for the questions. Point charges Q1 is equal to 1 nanocoulomb and Q2 is equal to 2 nanocoulomb are at a distance apart. Which of the following statement or statements is or are incorrect? We know that the like charges would be repulsive, right? It will repel. So definitely statement 1 is correct and it is not incorrect. And we know that 2 point charges would experience the same force, but of course in other directions. So the magnitude is definitely the same, and hence the second statement is also correct. So it is not incorrect. Okay, the third one, as the distance between them decreases, the force on Q1 increases linearly. Now we know that it is inversely proportional to the square of the distance. So the force would increase as the distance would decrease, but it will increase in a square, in a non-linear fashion, right? It is not linear fashion. That is why the third statement is incorrect. What about the fourth statement? A point charge Q3 is equal to minus 3 nanocoulomb located at the midpoint between Q1 and Q2 experiences no net force. No, definitely not. Definitely experience some force, and we have to do the calculations. So that is why the fourth point is also incorrect. So these are the two statements which are incorrect. Okay. Next, a point charge 30 nanocoulomb, minus 20 nanocoulomb, and 10 nanocoulomb are located at minus 102. Let me consider a cube for this. Okay. So let me clear this. Okay. So I have a cube, and yes. So let me first consider the cube and then consider those points. So let me consider the cube. So I am considering the cube x, y, and z. Say I have a cube. Let me assume. Okay, so we try to join. I think I should have written this first and then later that. Okay, let me try to do this. Okay, I think now it will be right. Let me assume that it is in the center. And what is the dimensions of the cube? The dimensions of the cube is 6 meters, right? So it is 6 meters. Now we know from the Gauss law that the flux is equal to the total charge enclosed, right? So psi will be equal to q. Now we should know what are the charges present within the cube. So we have to see the coordinates. So if you look at the coordinates, the first one is -1, 0, 2. So -1, 0, 2. So let me do this. So this is centered. So -1, 0, 6, right? So what will be these coordinates from the center if I consider? So this will be like 3, 3, 3. This end, the other end will be -3, 3, 3. So within this, if these values are there, at the other end, okay, the other exactly diagonally opposite end, 3, 3, 3. So -1, 0, 2 definitely will be within that limit. And the second one, so there's some technical issue. Okay, so 0, 0, 0, this is definitely within the cube. But what about this 1, 5, -1? This is not outside, this is not within the cube. That is, the third charge is not within the cube. The charges which are present within the cube is 30 nanocoulomb and -20 nanocoulomb, right? So, yeah, 30 nanocoulomb and -20 nanocoulomb. So 30 nanocoulomb minus 20 nanocoulomb is 10 nanocoulomb. So the answer is the 10 nanocoulomb. The answer for this problem is 10 nanocoulomb. Okay, now what about the third question? For the third question, let me turn on the camera. Okay, I hope you can see it. Okay, yeah. Let me try to explain. For this, you need to use the right hand thumb rule or right hand screw rule, right? Now, the magnetic field intensity is flowing in the outward in the anti-clockwise direction. So I'll use this anti-clockwise direction. The thumb is pointing towards me, which is nothing but the tail of the screw, which is correct. So this is correct. Similarly, this is also the electromagnetic field intensity is in anti-clockwise direction. So this is also towards me, pointing towards me. So this would be considered as positive. But whereas here, the current is going into the page. Like this is outside the page, this is inside the page. So current is out. So here it is inside the page. So it is in the other direction. So H dot dl is equal to total current enclosed, right? So 10 minus 30 is minus 20 amperes. So this is 10 amperes. This is minus 20 ampere. The 30 ampere is outside this. So it is not at all enclosing it. So I'm not considering it. So first one is 10. Second one is minus 20. So third one, it is this magnetic field intensity is not enclosing any current, and hence it is 0. So 0 amperes. Finally, fourth one, it is in clockwise direction. So it is into the page, but it is showing like outside the page, and hence it is minus 10 amperes. So the correct option is 10 amperes, minus 20 amperes, 0 amperes, and minus 10 amperes. Moving on to the next question, fourth question. So here again, we have to say which is not a correct representation. Earlier one, also we had to calculate the value of current. Here we are trying to calculate which is not a correct representation. Now, again, let us use the right hand thumb rule or the right hand screw rule. The current is pointing upwards, and you can see that the fingers encircling it is in the anti-clockwise direction, and the first one is correct. Second one is current is pointing towards you, so the magnetic field intensity should be in anti-clockwise direction. Therefore, this is also correct. B, right? Correct. Please use this. It is showing the tail of the screw, which is pointed screw. It is towards you. It is correct. What about the third one? The third one, current is rotating. Please observe, this is the current. So current is rotating. So, and magnetic field intensity inside the page. So if I use this right hand thumb rule, it is coming actually outside the page. It is outside the page, but here it is shown as inside the page with the head of the screw. So definitely this is third is wrong. But fourth one is correct because the current is going. So using the right hand thumb rule, you can say that you can see that yes, the fingers is pointing towards you, right? So it is towards you, and hence H is correct. And similarly, current is downwards, right? So if I use downwards at this side, from this side it is towards you. At this side it is inside, going inside the page. So this is also absolutely correct, and hence only C is not the correct representation. Finally, the charge Q is uniformly distributed in sphere of radius R. How is the charge density going to change if the same charge is occupying the sphere of radius R by 4? So let me go to the Jamboard. And first, what I'm trying to tell is, it was first occupying a complete sphere, right? That is what they have given, and some radius R. So now they are saying, well, how will the charge density change? We know that volume of the sphere is nothing but 4 pi 3 pi r cube, right? Okay, so that's the volume, right? So we know that the rho v is nothing but so charge by the volume, right? So Q by volume, right? Now volume is this. R is reduced. Definitely R is reduced by 4, and okay, so R is reduced. So one thing, when you say that R is reduced, of course, when R is reduced, the volume would reduce. And since volume is reduced, the charge density would increase. By how much factor? That's the question, right? So the how much factor? So 4 fours are, it is reduced by 4. So R is reduced by 4 times. But R is volume is proportional to the cube. So 4 fours are 16, 16 fours are 64. So by 64 times, the volume would increase. That means what, in that much space that you are trying to accumulate more amount of charge. So volume charge density would definitely increase, and it increased by 64 times. So the answer for this is it will increase by 64 times. And finally, the last question. The electrostatic potential due to a point charge Q1 at a distance of R is equal to 1 centimeter away from it is 1 volts. Okay. And what is the potential V2 of a charge Q2 is equal to 4 Q1 at a distance R2 1 centimeter from it. So let me take it. So we know that V is equal to Q by 4 pi epsilon into R, correct? So you have, say, suppose earlier Q is equal to, they've given for some particular Q and V. What you have to change? How is it changed, right? So Q is nothing but, with respect to Q1, it is 4 times Q1 and 4 pi epsilon naught. R is how much? R is 2 centimeters. So 2 times of it. Earlier R was 1 centimeter, now 2 times of it. So I'll just write 2 times of R. If I do this, it is 2 ones are 2 twos are. So it is 2 into Q1 by 4 pi epsilon naught into R, which is nothing but 2 times the initial value. So definitely, so earlier value is what? Earlier value is 1 volt. So 2 into 1 volt is 2 volts. So the answer is 2 volts for this. So I have tried to cover the electrostatics, the magnetostatics, overview of it, the early quiz and discussion of the early quiz. Now we will be dealing with the time varying fields, and the session will be continued by Professor Kavya AB Madam. Thank you.
Thank you, sir. Now we'll be starting with time varying fields. So we have seen what is Maxwell's equations for electrostatics and magnetostatics, that is static fields. We'll see the Maxwell's equations for the time varying fields now. So Maxwell's equation in point form and integral form. So this is for the time varying fields. So first Maxwell equation is from Gauss law. For the time varying field, it is given by del dot D is equal to rho V. The integral form is given by integral D dot ds is equal to integral rho V dV. So there will be a new term included in Faraday's law for the in the time varying field. So from Faraday's law, we can write del cross E is equal to minus dou B by dou T. Whereas for the static fields, del cross E is equal to 0 because there is no variation in magnetic flux density B. And similarly, closed integral of E dot dl results in 0. That is for the static fields. Whereas when we talk about the time varying fields, so for from Faraday's law, we can write del cross E is equal to minus dou B by dou T, and integral E dot dl is equal to minus integral dou B by dou T ds. So this is Faraday's law. And also Ampere's circuital law also, there is a change in the equation. So if you have, if you remember, for magnetostatics, we have studied the expression del cross H, that is curl of any expression del cross H is equal to curl of H is equal to J. Whereas here, along with the vector J, you will also have dou D by dou T. D represents the displacement current. So this is the change in the Maxwell's equation for the Ampere's circuital law. So del cross H is equal to J plus dou D by dou T. So if you take the integral form, it is H dl is equal to J plus dou D by dou T into ds. The last one is from Gauss law. It remains same for the static fields as well as time varying fields. Del dot D is equal to 0 or integral B dot ds is equal to 0. So this is in the integral form. So questions, some questions they have asked in GATE exam related to time varying fields. So they'll give the equations. You have to match with whether it is from Gauss law, Faraday's law, or like that. Or also they'll give particular equations, and you can check whether the fields satisfies the Maxwell's equation or not. So questions like that will be asked. And the next one is Maxwell's equation for free space. Again, this is for the time varying fields. The only difference here is in the first equation, del dot D will be equal to 0 because in free space, there is no charge. Rho V is equal to 0. And in the third equation, J is equal to 0. In the third equation, J is equal to 0 because J is given by conductivity into electric field intensity. So conductivity of a free space is 0, sigma is 0. So J becomes 0. So the only difference for free space and the Maxwell's equations is in this expression, J will not be present, current density, and here rho V is equal to 0. So the rest all remains same. So next, we have to talk about uniform plane waves. So this is one of the important topics on which questions will be asked in the GATE exam. So uniform plane wave, it is an EM wave in which electric fields and magnetic fields, they are mutually perpendicular to each other and also to the direction of propagation. So here you have to concentrate on the wave equation and the different parameters related to the wave. So first one is the velocity. Velocity is given by omega by beta. V is equal to omega by beta. The second one is wavelength. Wavelength is given by lambda is equal to 2 pi by beta. Third one is intrinsic impedance, which is given by eta is equal to E by H. The general expression is root of j omega mu divided by sigma plus j omega epsilon. For free space, this equation can be written as root of mu naught by epsilon naught. So if you're considering for other medium other than free space, you will have mu r divided by epsilon r. So otherwise it is root of mu naught by epsilon naught. The value is around 120 pi, or it is 376.7, nearly equal to 377. The next one is attenuation constant. So this is the general formula of attenuation constant, alpha. Similarly, phase constant, the general formula for the phase constant. Instead of the general formula, you can go through the formula for the attenuation and phase constant in different mediums. So that will be mainly asked. So how the wave travels in different mediums like perfect dielectric, good dielectric, and good conductor. So that will be discussing in the next slides. And the last one is propagation constant. The general formula is alpha, that is attenuation constant, plus j beta, phase constant. So these are the different parameters that just now we saw: attenuation constant, phase constant, velocity, propagation constant, and intrinsic impedance. And the value of all these in different mediums. So one is a perfect dielectric, another one is a good dielectric, and the third one is good conductor. So in all these different mediums, what are the parameters associated with uniform plane waves? So you might have derived all these equations. So this will help you in solving some of the problems on wave uniform plane waves. So in the perfect dielectric, attenuation constant alpha is equal to 0. For good dielectric, it is sigma by 2 root of mu by epsilon. For a good conductor, it is root of omega mu by 2. So similarly, phase constant for good conductor, alpha is equal to beta. For perfect dielectric, it is omega root of mu epsilon. And for good dielectric, this is approximated omega root of mu epsilon. Similarly, for velocity, 1 by root of mu epsilon. So this is for good dielectric, 1 by root of mu epsilon into this value. And here it is root of 2 omega by mu into sigma. And then phase constant, it is just the addition of alpha and beta. So alpha is 0, only the value of beta, alpha plus j beta. Similarly here, alpha plus j beta and alpha plus j beta. And the last one is intrinsic impedance of the medium. Eta is equal to root of mu by epsilon. This is for perfect dielectric, good dielectric, and finally good conductor. And problems related to Poynting's theorem and also calculating power, average power density. So those kinds of problems also you can see in previous GATE question papers. So Poynting theorem states that the net power flowing out of a given volume is equal to the time rate of decrease in the energy stored within the volume minus the ohmic power dissipated. This is the integral form of Poynt's law, of Poynting theorem. So P dot ds, it is the power, net power flowing, which is given by negative sign indicating decrease in the energy stored minus the ohmic power dissipated. So this minus sign and decrease in energy is given by the negative sign. The first expression, J dot E, represents the ohmic power dissipated. So J dot E represents ohmic power dissipated. So J is equal to sigma into E. Dot product J dot E is sigma into E square. So very much similar to V square by R. So this represents the ohmic power dissipated. And the second term, it is half epsilon E square plus half mu into H square, which is nothing but the energy stored within the volume. So power, net power flow is equal to the energy stored, rate of decrease in the energy flow minus the ohmic power dissipated. So this is Poynting's theorem. So from this Poynting's theorem, we have average power density, which is given by E square divided by intrinsic impedance of the medium, and the average Poynting vector is given by half into real part of E cross H. So this is average Poynting vector, which is given by half into real part of E cross H. The Poynting vector is given by E cross H. And under uniform plane waves, you should also concentrate on skin depth and loss tangent. So skin depth, it is defined as the depth in the conductor where the current density is just 1 by E times the value at the surface. So it is 1 by E times the value at the surface. So that is called as skin depth. And the skin depth is given by delta is equal to root of 1 by pi into f into mu into sigma. And the next one is loss tangent. So which tells you how the material behaves at different frequencies. So tan theta is, the loss tangent is represented by tan theta, which is equal to sigma by omega epsilon. So at omega in the denominator, you have 2 pi f. So depending on the frequency, the nature or the behavior of the system of the medium will also vary. So it will vary from being a good conductor to a perfect dielectric. So this loss tangent will give information about the properties of the medium. So based on this, we shall discuss some problems. The first one is given the time varying field, vector B is equal to 5ux plus 6uy minus 3uz cos of 5000 t Tesla and a square filamentary loop with its corners at 2, 3, 0, 2, minus 3, 0, 2, minus 2, minus 3, 0, and 2, minus 3, 0. So the resistance of the loop is 900 kilometers. You have to find the current flowing in the loop. So different options are given: minus 0.4 sine 5000 t amps. So similarly, option B is 0.4 sine 5000 t amps, and this is minus 10 sine 5000 t amps and 10 sine of 5000 t amps. So we'll see how to calculate this. Vector B is given here, and the points are given, and the resistance is given. So we can observe here, you have to calculate current. In order to calculate current, first you have to calculate the EMF induced. So this problem is on Faraday's law, which is given by E is equal to minus d phi by dt, where phi is equal to integral B dot ds. So B is given, we have to calculate phi, so that next we can calculate EMF. From that EMF will be calculating the current. So now let us calculate phi. So phi is equal to B dot ds. So integral B dot ds. So expression for B is 3 minus 3 cos of 5000 t minus 3 cos of 5000 t into ds. So ds can be written as magnitude ds vector. So here you can observe minus 3 cos of 5000 t. So everything is constant. So you can take it out of integration. So it is integration only with respect to ds. So integration with respect to ds, I can write the expression as minus 3 cos of 5000 t into integration with respect to ds is total surface S. So this is the expression for phi. which is equal to minus 3 cos of 5000 t into S. So now what I'll be doing is I'll calculate what is this area S. So in order to calculate the area, you have to consider the points given in the question. So they have given the points. First point is 2, 3, 0. Second point is minus 2, 3, 0. And the third point is minus 2, minus 3, 0. And the last one is 2, minus 3, 0. So from this, you can observe that it forms a rectangle. Area can be calculated as A is equal to or S is equal to. So this side is 4 minus of minus 4. Sorry, 2 minus of minus 2. So it becomes 4 into 3 and 3. So this length you can take. So 3 minus of minus 3 is 6. So area is 4 into 6. So it is totally 24. So now phi can be calculated. So phi is equal to minus 3 into 4 into 6. So it is minus 72 cos of 5000 t. So this is the expression for phi. So once you get phi, E can be calculated minus d phi by dt. So E is equal to minus d phi by dt. So we have to differentiate it with respect to t. You will get the expression as, so when you differentiate cos, you will get minus sine, minus sine into 5000. So you will get it as 72 into sine 5000 t into 5000. So once you get E, you can calculate current from this. So this E is nothing but the EMF induced. So this is the voltage. So once you get voltage, so current is equal to V by R. So R value is given 900 kilo ohms. So 72 minus 72 into 5000 divided by the value of R is 900 kilo ohms. So if you divide by this into sine, so if you divide, the answer will be minus 0.4 sine of 5000 t amps. So this is how you can calculate current. So the first option is the correct one, minus 4 sine of 5000 t amps. So this is the expression for current. So coming to the second one, it is given, consider the figure shown below. Let B is equal to 10 cos 120 pi t Weber per meter square, the value of VAB and I of t. So you have to find the EMF induced as well as the current here. So this is the figure given. You have uniform magnetic flux density B, and the resistance is given 250 ohms. It is from point B to point A. So you have to find what is voltage as well as current. So it is similar to the previous one, that is based on the Faraday's law. So again, E is equal to minus d phi by dt, where phi is given by integral B dot ds. But since the field is uniform, you can consider that the field is constant at everywhere, and you can take B outside. So integral ds, B integral ds. You can observe in the figure, it is a circle with radius rho is equal to 10 centimeters. So when you integrate throughout, when you integrate with respect to ds, you will get the total area. So since it is a circle, you can take it as pi r square, where the value of r is the radius 10 centimeters. So this will be equal to B into pi r square. So the rest is same. So you can substitute for B and then multiply by pi r square. The expression for phi will be 0.31 cos of 120 pi t. So once you get the expression for phi, E is minus d phi by dt. So when you differentiate this, the answer will be 118.43 sine of 120 pi t. But this EMF induced, whatever we are calculating here, it is from B to A. B is the initial point, A is the final point. So what you have calculated is VBA of t. So this is the EMF induced VBA of t. So what is asked is you have to calculate VAB instead of VBA. So you have to reverse this direction. So you will get E is minus of VBA of t. So even though we have got 118.43 sine of 2000 pi t, since in the question it is asked VAB instead of VBA, you have to take the negative sign. So this option is the answer. So since you have got sign here and this is also sign, but this is positive, directly you can choose the option C as answer instead of calculating current I also, because this is the only option where we get the value of voltage as minus 118.43 sine of 120 pi t. So if you want to calculate even current as well, so the resistance is 250 ohms. It is nothing but voltage divided by resistance. So current is E divided by R. So our value of R is 250 ohms. So it comes to around minus 0.47 sine of 120 pi t. So this is the value of I. So option 3 is the correct answer. So next question, different field equations are given. The following field exists in charge-free regions. P is given, Q vector is given, R vector and S vector. 4 vectors are given. You have to determine the possible electric fields. So again the options are here given here. PQ vector fields or RS or PR or QS. So these are the 4 options given. So in this question, you can observe the condition is charge-free region. So you can assume it has free space. So you can take this region has free space. So for free space, the first equation, that is from Gauss law, you have del dot D is equal to 0. So this is the expression for free space. So in general, if you're writing, I can write it as del dot A is equal to 0. Similarly, second expression from Ampere circuital law, del cross H is equal to dou D by dou T. So that means del cross H is not equal to 0. So for free space, divergence del dot A should be 0, curl del cross A should not be equal to 0. So these two conditions you have to check in order to check whether these are possible electromagnetic fields. So del dot A should be equal to 0, del cross A should not be equal to 0. So you have to calculate del dot A or del dot P for the first case, check whether it is equal to 0 or not. Similarly, you have to calculate del cross P and check whether it is not equal to 0 or not. Similarly, you have to do it for Q, you have to do it for R, and you have to do it for S. So when you do it, you will get del dot P for the first one, del dot P is 0, del cross P is not 0. Similarly, if you do it for the second one, del cross Q is not equal to 0, whereas del dot Q is 0. Whereas for the other two fields, del dot R. So if you calculate del dot R, so del dot R for the vector field R is not equal to 0. So this will not represent an electromagnetic field. Similarly, for the fourth one, if you calculate del dot S, so del dot S Again, if you calculate that, it will not be equal to 0. So from this, you can come to the conclusion that the first two, that is P and Q, are possible electromagnetic fields. So you have to calculate divergence and curl for the two equations and check whether they satisfy the Maxwell's equation or not. So P and Q are the one which satisfies the Maxwell's equation. So they represent the possible electromagnetic field. So next question. When a non-magnetic medium, vector E is given. So this is the expression for a uniform plane wave. So it will be in terms of sine, cos or e power form. So vector E is equal to 5 cos of 10 power 9t minus 8x ax cap plus 4 sine of 10 power 9t minus 8x az cap volts per meter. You have to find the dielectric constant of the medium. So these different options are 3.39, 1.84, 5.76 and 2.4. So this can be calculated using the formula V is equal to omega by beta. So we should know what is the value of omega and what is the value of beta. So from this equation, so the standard form of this equation is 5 cos of omega t minus beta x. So omega value will be 10 power 9, beta value will be 8. So omega is equal to 10 power 9, beta value will be 8. So from this expression, we'll get the value of omega and beta, and then we can calculate the 9, and the value of beta is 8. We can also write the expression for V. So V can be written as V is equal to 1 by root of mu naught mu r epsilon naught epsilon r. So since it is a non-magnetic medium, mu r will be equal to 1. You have to find the value of epsilon r, that is the dielectric constant. And root of 1 by root of mu naught into epsilon naught is nothing but the velocity of light. So this expression further you can write it as c divided by root of epsilon r. So c is nothing but 1 by root of mu naught into epsilon naught. So you can use this equation. V is equal to omega by beta, you will get some value. And again V is equal to c divided by root of epsilon r. So c divided by root of epsilon r is equal to omega by beta. The value of c is known, omega is known, beta is known. So you can calculate the value of epsilon r, which comes around 5.76. So this is the value of epsilon r. That is the dielectric constant of the medium. So in a non-magnetic medium, the dielectric constant of the medium is 5.76. So coming to the next one, a uniform plane wave is given. A uniform plane wave in free space has electric field. Vector E is equal to 2ax plus 3ay e power minus j beta x volts per meter. We have to find the magnetic field. So magnetic field, different options are given. So we have to find what is the expression for magnetic field. Electric field. So the relation eta is given by, that is intrinsic impedance is given by, eta is equal to E by H. So H is equal to E by eta. So H is equal to E by eta. So eta, you can it is given as free space. You can consider the value of eta as 120 pi. The value of eta is 120 pi. Now we have to write the expression for E. So E expression is given by vector E is equal to 2ax plus 3ay e power minus j beta x. So if you are observing this expression, from this expression, we can tell the direction of propagation is x. So e power minus j beta x. So this x represents the direction of propagation. So x is direction of propagation. And vector A is given by this expression. So we have to write what are the unit vectors for vector H. So in order to write that, you can consider unit vector of electric field cross product unit vector of magnetic field should be equal to the normal direction, that is direction of propagation, which is given as x here. So AE cross AH should be equal to AX. So this is AZ. Two AZ plus 3AY e power minus j beta x. So 2 AZ so from first case, this is AZ cross product AH should result in AX cap. So when you take AZ cross product with a unit vector, the answer should be AX cap. So I can take it as AZ cross minus AY, it will result in AX. So first vector is AZ. So if you take AY, the cross product will be minus AX. But since the cross product should be AX cap, so AZ cross minus AY will result in AX. So this is the first unit vector that we have got for AH. So for the first case, AH should be equal to minus AY. In the second case, we have 3AY. So this is the AE cross AH should be equal to AX. But in the second case, AE is AY. So AY cross AH should be equal to AX. So in place of AH, if I have AY cross, if I have AZ, then the answer I'll get it as AX cap. So AY cross AZ will give me AX. So vector AH is equal to AZ. So in the second case, vector AH is AZ. So now if I write the expression for vector H, it is 1 by eta. So first one is minus AY. So minus 2AY, because in electric field we have 2, but sign is minus AY now. The second one is 3 multiplied by AZ into e power minus j beta x. This is the expression for vector H. So vector E is given as 2AZ plus 3AY. So now I have modified it for vector H. So 2 into minus AY plus 3 into AZ. So this becomes 2 into minus AY plus 3 into AZ divided by eta into e power minus j beta x. So the value of eta is 125 for free space. So once you divide it, the answer will be minus the last option minus 5.3 AY plus 8 AZ e power minus j beta x milliamps per meter. So this is the option for the fifth one. Fifth problem. So the option D is the answer. So this is how you have to calculate vector H if vector E is given. So always in uniform plane wave, electric field and magnetic field, they are perpendicular to each other, and also they are perpendicular to the direction of propagation. So from this, you can calculate vector H. So next one is also a question on a plane wave. So there is a plane wave having dielectric, having electric field component E is equal to 8AX plus 6ay plus 5az e power j omega t plus 3x minus 4y volts per meter. It is incident on a perfectly conducting slab positioned at x greater than or equal to 0. What is the electric field of the reflected wave? So incident wave equation is given. So it is asked to calculate what is the expression for the reflected wave. So vector E is given. So there is a perfectly conducting slab. Okay. So whatever wave is incident on this, it is not transmitted. It gets completely reflected. So it will get completely reflected. So this is the incident wave EI and this is the reflected wave. So now if I consider this as x is equal to 0, this term has x is equal to 0. The region below this is x less than 0 and the region above this is x greater than 0. So incident wave and reflected wave, they are the magnitude of both remains same. Okay, the equation remains same. Only thing is, since it is not getting transmitted, complete EM wave is getting reflected. So your reflected wave is same as the incident wave, but the value of x will change. So here the x is positive. So here the value of x will become negative and the entire magnitude becomes negative. So minus. So expression. So just by observing the waveform, you can write the expression for just by observing the figure that I have written, you can write the answer for this. That is vector E is the expression. So total amplitude, total this magnitude multiplied by minus sign. So minus 8ax minus 6ay minus 5az you should get. And here the wave is getting reflected. So the sign changes from the sign of x changes from positive to negative. So plus 3x should become minus 3x. So this is plus 3x. So this is plus 3x. So it should become minus 3x. So the rest is all same. Here you have to multiply it by minus. So magnitude is minus. Then you have to multiply by, you have to change the sign of x to minus 3. So minus 8ax minus 6ay minus 5az into e power j omega t minus 3x minus 4y volts per meter. So this is the option for the answer. Since it is perfectly conducting slab, incident wave and reflected wave will have same value, but in x value is in opposite direction. Coming to the seventh one, it's a very simple problem. So they have given, consider the figure shown below. You have to find angle theta T1 and theta T2. There are three mediums here. One is free space. And two mediums here. This is medium 1, which is having the value mu r is equal to 1 and epsilon r is equal to 4.5. In this region 2, mu r is equal to 1 and epsilon r is equal to 2.25. So you have to find the value of theta T1 and also theta T2. So this can be determined using the Snell's law. So we'll see how to do this. The Snell's law is given by sine theta so medium 2 angle is theta T1 divided by medium 1 angle is sine of theta I. So incident angle, which is equal to velocity V1 by V2. So I can write velocity as c divided by root of mu r into epsilon r. Similarly, c divided by root of mu r into epsilon r. So here it is mu r1 epsilon r1. Here it is mu r2 epsilon r2. So sine theta 1, sine theta T1 divided by sine theta I is equal to V1 by V2. So this expression I can write it as root of epsilon R2 divided by epsilon R1. Because mu R1, mu R2, they have given the value of mu R2 and mu R1 as 1. So you'll be left with only epsilon R1 and epsilon R2. C gets cancelled over here. So sine theta T1 divided by sine theta I is equal to root of epsilon R2 divided by epsilon R1. So in the figure you can observe the incident angle is given 45 degrees. In this region, the value of epsilon R is 4.5. So for free space, you can take the value of epsilon R as 1. So you know the value of epsilon R2, epsilon R1 and theta I. From this, the value of theta 1 can be calculated. So theta 1 is equal to 19.47 degrees. So 19.47 degrees is the only option present in point B. So if it is present in 2 or more options, then you can calculate theta T2 as well. If it is present only in one option, you can directly select this as the option, select this as the answer, because the first one what we have got is 19.47. So if it is present in 2 or more options, same answer is given, then you can calculate the second theta angle. So here also you will consider the Snell's law. So that is sine theta T2 divided by sine theta T1 is equal to root of epsilon R2 divided by epsilon R1. So now this becomes medium, second medium, and this is the first medium. So epsilon R2 is 2.25 and epsilon R1 is 4.5. If you calculate the second angle, so theta 1 is calculated in the previous step. If you calculate second angle, it comes to around 28.03 degrees. So this is again a uniform plane wave, but they have asked to calculate the angle of incidence. So this is the second option is the correct answer. Coming to the next one, here vector H is given. It is in amperes per meter. The H field in ampere per meter of a plane wave propagating in free space is given by vector H is equal to 5 root 3 divided by eta naught cos of omega t minus beta z ax cap plus 5 by eta naught sine of omega t minus bz plus pi by 2 ay cap. You have to calculate the power here. The time average power flow density in watts is, the 4 options are given. So let us see how to calculate the answer for this. Power is given by the expression E cross H. Vector E cross vector H. So you can substitute for vector E, which is eta naught into vector H. So when I take only the magnitude of this power, I can write the expression as eta naught H square. Magnitude of vector H. So that is H square. So eta naught into H square you will get. So square of magnitude of vector H. Average power is given by the expression eta naught by t 0 to t H square dt. So you have to take the magnitude of H and square it. So H is having 2 terms, one is x term and another one is y term. So you'll get it as Hx square plus Hy square dt. So eta naught divided by t 0 to t Hx square is, so when you square it, you'll get it as 25 into t. It is 5 root 3. So 25 into 3 divided by eta naught square cos square omega t minus beta z plus Hy square is 25 divided by eta naught square sine square omega t minus beta z. You have to differentiate this with respect to, you have to integrate this with respect to t. So how to solve this means the sine square of omega t minus beta z pi by 2. You can expand this expression using sin A cos B formula. Sine of A plus B is equal to sin A cos B plus cos A sin B. So when you expand this, sin A is omega t minus beta z, cos B is cos of pi. So first term becomes 0. So second term, cos omega t minus beta z, sin pi by 2, it becomes 1. So cos of pi by 2 is 0, sin of pi by 2 is 1. So this expression can be written as t is equal to eta naught by t, eta naught square is common, 0 to t. So 25 into 3 is 75. So 75 cos square omega t minus beta z plus 25. First term becomes 0. So second term is omega t plus beta z. So cos omega t plus beta z. So it is under, this is, the whole thing is square. So now you can square it, cos square omega t minus beta z dt. So this is the same expression. You can add it, you will get 100 cos square omega t minus beta z. So again, t will be equal to 1 by t eta naught into integration 0 to t 100 cos square omega t minus beta z dt. Again this you can expand it, 1 minus 1 plus cos 2t. So finally you will get it as 100 by theta eta naught. So this, when you expand this, you'll get into 1 by 2. So from this, you'll get 50 by t eta naught. So this is the value of average power, 50 t by eta naught. So that is the last option. Time period, when you integrate it, that gets cancelled. So final answer is 50 by eta naught. So this is the time average power flow density, which you have to calculate. And the last one, question number 9. So here also you have to calculate the power. So electric field component of a time harmonic plane EM wave traveling in a non-magnetic lossless dielectric medium has an amplitude of 1 volts per meter. If the relative permittivity of the medium is 4, the magnitude of the time average power density vector is, so 4 options are given, 1 by 30 pi, 1 by 60 pi, 1 by 120 pi and 1 by 240 pi. So E is given, E is equal to 1 volts per meter. Epsilon R is given 4 and it is a non-magnetic medium. So mu R is 1. So average power density vector, average power density is given by E square by 2 eta. So E square divided by 2 into 120 pi is for free space. So eta can be written as 120 into root of mu r by epsilon r. So this is just a substitution for substituting for epsilon r, it is 4. So 1 divided by 2 into 120 pi divided by 1 by 4, which is 1 by 2. Root of 1 by 4 is 1 by 2. So 2 gets cancelled. So final answer is 1 divided by 120 pi. So this is the answer for the last one. 1 divided by 120 pi. So this completes the session on electromagnetic waves. So end quiz will be shared. The link will be sent to you all. So kindly attend the end quiz. So we'll end the session here. Thank you all.
Thank you all for attending the session. If you have any doubts related to the first part, okay. So if you have doubts regarding the first part, that is the static electric and static magnetic fields, feel free to contact me. This is my mail ID, Sandeep.ECE at the rate VVCE .ac.in. Okay, I could have typed it right. Yeah, I think I'll type it for better clarity. Sandeep.ece at the rate vvce.ac.in. Yeah. Okay, next, if you have doubts regarding the time varying fields, that is the Faraday's law, Poynting theorem, skin depth, uniform plane waves, and all, you can contact Kavya madam. Yeah, thank you so much for attending the session. All the best for your exams. Thank you.